Hi everyone. That was a quite quick change, but let's see where we can take this. Hi, I'm Philipp. I want to talk a bit about search and what you can do with search. So I guess everybody here is using databases, right? Yes, good. Who is using search already? Anybody using search, public search, and not just Google search, but like your own built-in search? Anybody? Okay, let's see. So I always compare search, like this is the database side, this is the search side. Databases are very good at black and white search. You basically have like, something is a hit, something is not a hit. That is the general idea. It's very black and white. You find exact matches. Yes, you can do a like search, but it's not very performant. Whereas search is more about these shades of gray, where it's maybe not reality, but you have like more like finer shades. Like for example, you search for a concept like hoodie, but you don't care about if it's hoodie or hoodies in singular or plural. It's just you're generally interested in the concept, and then you have these shades of gray searching for that. Why am I talking about that? Well, I work for Elastic, the company behind Elasticsearch. Anybody heard of Elasticsearch? Good. We seem to be doing our job then. If you're searching on any of these sites behind the search box, there is Elasticsearch doing the search. So, including Wikipedia, Stack Overflow, GitHub. Behind the search box, there is always Elasticsearch doing search. And well, I work for the company. My official title is developer, advocate, avocado, whatever. I basically don't work, I just travel and speak about what we do and build demos or answer questions or do stuff like that. Whatever is fun. So generally, what is the difference between a database and full text search? The main difference is that you do different stuff or more work when you store information. So we have a Lucene library in the background that is storing the thing on disk, so there is no other data store, because sometimes people ask, like, what is the database behind this? There is no other database. There is Apache Lucene, which is the library that writes to disk. And then Elasticsearch is what you're talking to. It has generally a REST interface. You just speak HTTP to it, and that's storing the search there. So who remembers Star Wars and knows what is the sentence when he makes this hand movement? Who watched Star Wars, the originals, recently?
These are not the droids you're looking for.
Yes, exactly. These are not the droids you're looking for. And we want to take this one sentence and see how Elasticsearch actually analyzes that sentence. So that is the original sentence. The thing you do first normally is you kick out any formatting. So because we had this emphasis around the not, for example, nobody's going to search for emphasis tags. Like nobody searches for like this is bold or this is italic or whatever. You just pick out any formatting and then you're left with these are not the droids you're looking for. The next step then is you standardize. Standardizing in Western languages is very simple. Basically, any punctuation marks or white spaces, and you can see there is a bit more space here, the dot is gone, you basically cut off stuff at different words. This is basically tokenizing down to words. In Western languages, this is pretty simple. If you have Chinese, Japanese, stuff gets more complicated. But I have no idea about those languages, so let's skip that for today, and let's stick to Western languages. Then we lowercase everything. Generally, also when you search in Google, you don't really care about upper and lowercase. And well, it's different characters, and you would need to search for any possible combination, so generally you just lowercase everything. And when you search, you also lowercase everything, and then you have just direct matches, and you don't care about the casing anymore. Then we remove the so-called stop words. Stop words are just very common words that appear in pretty much every sentence. Why do you do that? Because it would just blow up your index, and there's not much value in that. So you can see these are not there. These are all stop words. These are all kicked out. So what we're being left with is basically droids, you looking. And you can also see one other thing. It's not like natural language processing or like semantic search or something like that, because the not makes a difference, but it's a stop word. We're just looking for the concepts afterwards. So basically, when you search for it afterwards, you will search for droids you looking. And we don't actually do that, but we have one more step, which is the Snowball Stemming. And the stemming is basically reducing the words down to their root. So you don't care about singular, plural, you don't care about look, looks, looking. You just care about the concept to look, basically. And that is what you're extracting. And then you do the same thing for your search terms, and then you can just look for direct matches. You don't care about is droid like upper or lowercase, is it singular or plural. You have a direct match on this lowercase droid word, which makes the search very efficient. So we analyze every text that comes in according to the rules that you set up, And that's what you're actually storing. And that's what makes search much more efficient for this search use case than a database. So you can actually try it out. We have an underscore analyze endpoint where you say, this is an English sentence, and then it gives you exactly the same thing. And just to show you if my demo is working, let's see. So we have Elasticsearch running here. Here I hope is that readable for everybody? Let's make it slightly larger. Hope this is not too large. So we have our sentence here. These are not the droids you're looking for. And then when we run that through the analyzer, it gives you those 3 tokens that I've shown you before. So you can see droid, view, look. It also gives you some other information that will be helpful afterwards. So it knows the position. The position is helpful if you search for a phrase. So for example, if you search for droid view, which admittedly is a weird phrase, but since we extract that information, we have in our index, we can store the token droid and view, and we know that one is followed by the other, and that makes phrase searches very efficient afterwards. We also know start and end offset. That is, for example, if you want to highlight where is your match in a very long term, or in a very long sentence or text, we don't have to actually parse the sentence again, but we just know this is the start and the end point, and then we can just set the markers to highlight wherever your hit is. So that makes it also very efficient to do that. You could customize that a bit more. Here, for example, we say, okay, kick out the HTML, use the standard tokenizer, lowercase everything, remove the stop words, stem with the Snowball Stemmer, and then use the sentence that we had initially, and that's doing exactly the same thing. So that's what you would expect, but you could customize any step. So for example, in some situations, it might not make sense to remove the stop words, because you assume stop words make sense for you. So we've seen that example. The list of stop words is actually very short in English, but this is more of a linguist problem. Like the linguists will determine, like for this language, these are very common words that don't carry much meaning. We just pick them out, and it's like 33, 35, something like this. It's very well hidden in the source code, but this is the list of the words that we will remove. Should you always use stop words? Yes, no. The answer is always it depends. But for example, here, to be or not to be, everything is a stop word. You would never be able to find it if you use stop words on that one. So it really depends on what you're searching for. We do support a lot of other languages. We are missing Slovenian and Slovakian, which is kind of like the Austrian neighboring countries that are missing here. But most of the common languages, I think we do support here. And you obviously have language-specific rules. For example, the is, has, or possessive in English, we just kicked it out. In French, we could kick out like the article in the beginning and the accent. In German, generally we assume the umlauts don't make much difference. We just kick out any dots, and that special S thing is just a double S, because we assume it doesn't make much difference. In some languages, the umlauts don't make a difference. For example, in Swedish, they also have an umlaut A, and there it seems to be a totally different letter, and there the analyzer keeps it. But this is again a linguistic problem, and linguists make up the rules, and then you just put them into code to do the right thing for you. So, this should be the right sentence for German. I hope most of you speak German, but I think you do. So what will remain if I analyze that sentence? Any guesses? Yeah, in German is Droid den Such. That's what remains here after stemming. So this would stay in the index. If you use the German sentence and the English analyzer, obviously it will not work well. You can see here it assumes this is a plural, and it will cut off the S, but otherwise it just stays the same. So you will need to use the right analyzer for the right language, otherwise it will not work out. You also have a list of German stop words, which are longer and also very well hidden, but yeah. So what will remain here? Obi-Wan never told you what happened to your father. Any guesses? So you will get Obi-Wan, because with the standard analyzer, the dash is interpreted like we will break it into 2 tokens, never told you what happened to your father. So here, just by coincidence, we don't have that many stop words. So here pretty much the entire sentence almost stays.
Sorry, why is it told not hell?
Because it's not lemmatized. It doesn't know, like, it's not a dictionary. It's really just rule-based, and there is no rule to turn tell to told. The thing is, Dictionaries would make the results better, but there are generally no free dictionaries available because, well, it's a lot of effort to build those dictionaries and have them, and that's why there's no, like, the right license. It's very hard normally to get the right, good dictionary. There are if you pay. Normally they're from universities, because universities have cheap labor, students, and they build those dictionaries. And that's why oftentimes you get pretty good dictionaries from universities. But generally, what search does is, it's rather stupid. It just has a few simple rules, but that also makes it scale very well. But good question. But yeah, we don't have a dictionary, so we don't know the connection between L and O. Also, is and are not reduced down to B, for example. There are no rules for that. What will remain here? I am your father. No, I am your father. Actually, it's just I am your father, because the no is the only stop word. Doesn't understand really the meaning of the sentence, but it just works on the tokens. And what you can get is a so-called inverted index. So this was the first sentence, second sentence, the third sentence. And basically we extract all the tokens, like stop words removed, stem, the stemmed tokens, and we know how many times and in which position do they appear in every document. And this will make your search very fast afterwards, because when you search for something, it will run through the same analyzer. So for example, if you search for droids, it would also be, your search term would be stemmed down to droid. Then it would, in that alphabetically sorted list, it would go to, okay, here's droid. In which documents does droid appear and in what position? And then you could very efficiently find that position, highlight it, or find a phrase. That's the general idea of search. So to store everything, we can make that slightly more complex. Actually, we do have something that is similar to a schema. So what I'm doing here is, first I'm defining some synonyms. So I assume that father and dad are a similar thing. But I assume that every droid is a droid and a machine, but not every machine is a droid. So this is basically a replacement. So droid is expanded to droid and machine, but machine is not expanded to droid, because kind of not the same thing, hopefully. Then I can define my analysis pipeline, and at the very end, I add my synonyms here. So here, that is what I've called my synonyms. This is what I've defined up here. So I define my synonyms. At the last step, I set those synonyms. This whole analyzer I call my analyzer. And then you can see here, I basically say, there is a field called quote of the type text that uses my analyzer. Pretty much like a schema definition. But you will start valuing SQL more once you need to type all the curly braces. It's just like a different syntax. So if you insert that, you can see, okay, we have the mapping, and it tells you this is pretty much like a schema. We have this field code, and then we can just insert our 3 documents. Let me just quickly insert the 3 documents, and now we have stored. No, this was just 1. You as well. And then you can retrieve those. So you could just retrieve the entire document. You see, I just put it like these are just the HTTP verbs. This is pretty much like a REST call. Under the index Star Wars, I have a document with the ID 1, and then you get back all the metadata plus the source document. You could also just retrieve the source. This is pretty much what a relational database could give you, where you just say, like, retrieve me the original thing that you have stored, and it's just giving you JSON back. But that's not really the strength of full text search. You're not living up to the full potential. Let's start with searching, proper searching. What is the SQL equivalent of this query here? Any guesses? Yes, select star from Star Wars, basically. This just should give you all 3 documents back that you have inserted. And you can see here, in total we have 3 documents, and then down here you see all the 3 documents that we have inserted before. Let's do some searching. So let's assume we search for droid. Will you find anything if you search for droid? Yes. So you find the droids, these are the droids you're looking for. Will you find something if you search for droids in the plural? Yes. Yes, because the search term goes through the same analysis as the search, the terms that you have stored. And that's why you have always this direct match, and this will also find something. If you search for dad, will you find something? Yes, because we have defined the synonym for father and dad. And it will actually find all the documents exactly as if you had searched so it will give you exactly the same result. If you search for machine, how was that droid and machine thing? Will you find something or will you not find something?
Yes.
Every droid is a machine, but not every machine is a droid. Yes, you will find this. The droid is basically a machine, like we're searching for all the machines, and we're finding this one. Hopefully clear so far. We can also search for phrases, so if I say, I am your father, instead of a query match, you have a query match phrase, this will find the entire phrase for you. What happens, you can also add something here like a slop factor. A slop factor tells it basically if there is something in between in the phrase. So everything in the search term needs to be in the document, but there could be something more in between in the source document that you don't find. So if I search for I am not your father, with that sloppiness or slop factor, like if I set it to 0, nothing will be found. That's kind of the default. You could also say like there could be a minor variation, but everything in my search term has to be in my source document. Weirdly enough, I'm finding a document here. But if I say I am, let's say I am your loving father, then it doesn't find anything. Why did it find something when I had I am not your father? Why does this one find something?
Because it is a stop word.
Yes, exactly. What you basically do is you analyze the input here. This is a stop word. So basically you have like the tokens here, 0, 1, 2 is not there, 3, 4. And then with that sloppiness of 1, we basically say there can be the difference in counting, like all the tokens here need to be there, but there can be like one position missing, and that's why this is still a match. But it's kind of like you need to know like how stop words work and how sloppiness works, so this puts some good concepts together here. You also have some concept like fuzziness. So if you don't remember how to spell OV1 and I misspell it as fun, it does find something because, well, the auto fuzziness basically says it's a Levenstein distance, so basically edits. This would be a Levenstein distance of 1. So one letter could be too much, missing, or different. So you can just do fuzziness. You could also do fuzziness explicitly on the number, but auto would tune the fuzziness to 0, 1, or 2, depending on how long the search term is that you're searching for. If I search for OV1, so I misspell both terms, and I have a fuzziness of 1, will this find something, yes or no?
Yes. No.
It depends. No, here it doesn't depend. It does find something because fuzziness is on a per token level. With the standard tokenizer, this is broken up into 2 tokens, so we have a fuzziness of 1 each, and then we still find it. But that's something you just need to know how they're combined. So, we have been talking a lot about how stuff is being found, but we always had this score here. This is basically the quality attribute. How well does this document match my search query? Should this be returned or not? The question is only like, how do I calculate this long number? It looks kind of complicated. Where does it come from? Let me quickly jump to that part. By the way, if you want to do fuzziness in the relational database, good luck. And especially leading wildcards will never use an index, so this will also not be fast, so don't do that. Okay, so coming down to the score, how is that score calculated? Because it's kind of very central to what search does. It has a very fancy name, it's called TF-IDF if you search for one term, though actually the actual algorithm has now been replaced by something that is called BM25. This is best match 25, this is the 25th iteration of the best match algorithm. Maybe at some point we will have BM30 or whatever. But this is coming from academia, like things that have been tried out, and this one improves search. So you have 3 main parts in full-text search that make up relevancy. The first is the term frequency. Basically, if you search for father and one document contains father 3 times, it's more relevant than a document that contains father only once. I mean, it kind of makes sense. So basically, this is the number of occurrences, this is the relevancy, and this is the number of occurrences. So you assume if father appears once, it's not that relevant. If father appears 5 times in one document, it's more relevant. Between the the classical TF-IDF and EM25, you can see the difference is TF-IDF assumed, well, if it is appearing 20 times or 50 times, it's still a difference. Whereas BM25 assumes, well, once it appears 5 times, it's not much difference anymore. But the general idea is if a document contains your search term multiple times, it will be more relevant. Then you have the inverse document frequency. The inverse document frequency is over all the documents that you have, how common is a word. Or basically, to invert that logic is, it's dampening like very common words and boosts up less common words. So you assume this is how many times does a token appear over all your documents. So for example, father appears 20 times in Star Wars, I don't know, this is made up, but maybe, then it's very relevant. Whereas other words that might appear like hundreds of times, so for example, stormtrooper might be less relevant because it appears very frequently. You just assume what is rare is kind of more valuable, and rarer terms will have a higher score than very common terms. And then you have the final piece, which is the field length norm, which is very intuitive. If your search term appears in a short field, like a title, it will be more relevant than if it's in a very long field, which is intuitively kind of makes sense. So if I search for father, you could add and explain to the query, and then it will actually show you how it calculated why it got to that specific score. So if you look into that, it would then tell you, okay, here actually we found a synonym, dad and father, either one of them would work here. You can see the frequencies, the term frequency, and the value of that. You basically get the calculation for every single part of the TF-IDF algorithm and see why something has a specific value, and then you could debug that. So, if I search for father, this document is more relevant than this document. Why?
It's shorter.
Yes, the term frequency is the same. Both contain father ones. The inverse document frequency is also the same because father across everything. The only thing that is different is that this is slightly shorter than the other one, but you can also see in the score, like the difference is not that major. It's rather compact. All of this was only true if you searched for one term. What happens if you search for multiple terms, especially if some documents contain only parts of the terms you're searching for? Let's assume, this is now a bit made up, but let's assume we search for your father. And we assume that your is very common, so it has less relevancy than father, which is very rare in the Star Wars ecosystem and is more relevant. And the ideal document would contain your father. This is basically this vector here. And then the question is a document more relevant if it just contains father, or if it just contains your? And for that, you can draw their vectors like these are the documents that contain just your, and the documents that just contain father, and then you calculate the angle, and the shorter or the smaller the angle is, the more relevant the document is. So the ideal documents contain both your and father. Then you would have the documents containing father, and only then the documents only containing your, which also makes sense. And if you have 3 terms, then it would be 3-dimensional. And this is basically you search for n terms, and you have an n-dimensional vector then, where you see what is more relevant. We also have the so-called coordination factor. So for example, if you search for 3 terms, if all of the terms are there, you will not just add up the score, but you will basically reward if more terms are there. So you can see, since we're searching for 3, if only 1 is there, it's times 1/3, 2/3 of the terms, or 3/3 of the terms are there. So we will reward more terms in there. And then you can put that all together into the so-called practical scoring function. I'm never sure how practical it is, but this is what it looks like. You could also say something like a specific term is more relevant than others, and you can boost that term. But otherwise, we're just putting together the pieces that you've seen before. And luckily, Elasticsearch or Lucene will calculate it for you, and you don't need to do that in your head, because all the steps can kind of get a bit complicated then. You could also customize it with the function score, like you could have something based on geography. This is what, for example, if you search for a restaurant, it could include like closer places should be ranked higher. For example, I think Tinder is based on Elasticsearch, where everything is distance-based as well. They do something like that. Or it could be date-based. For example, if you have a newspaper, you might rank news from today and yesterday much higher than from a month ago, because, well, it's more news. You could also, the simplest one you could use is when you use a random score, where you basically give a random score to whatever you're searching for. Just to quickly demonstrate that, here, if you search for that one, you can see, no, I am your father has 0.5, and depending on how many times you run that, the order will change and the score will also be just random. This is very helpful if you sample data and you just want to have the sample data or 10 sample documents out of thousands of documents. Or if you have a booth and you need to do a giveaway, this is how we raffle the prizes that we give away. So we'll put all the people participating in the prize draw into Elasticsearch, and then we'll draw a random winner. Okay, and before I finish up, there's one other thing that people often try to do, which fails. Don't do this. There is this compare scores and say like, I want to say a score is something in percent. This is a perfect score, 100%, or this is a 50% score. The documentation actually even has a page that says that you should not do that because it's a very bad idea, but people still often try. And I can also show you why this might be a bad idea. So let's assume we have the sentence, these are my father's machines. What are the tokens that remain after analysis? Yeah, what you get is my father, dad, you can see here, synonym word, machine. And E stand away, and so this is what you would expect. So when we store that, let's store that, and then we say we search for my father machine. You could say this is like a 100% match, right? We have all the 3 tokens basically that we extracted and stored are there. So if we search that, we will get these are my father's machines has 2.9 something, and this has 0.8 whatever. So we could say this here 2.9, this is like a 100% match, right? Makes sense? Then the thing is, what happens if you delete that document and you search again? Is now the best match, now the best match would be 1.2 something, is that now a 43% match, or is that your next 100% match? And then the next step would be, this is maybe made up, but assume you have the term or the text, these droids are my father's machines, and you can see we have the term frequency, we have the terms multiple times now, and we search for those, then you suddenly would have 3 point something, and then you suddenly had a 103% match. That's why it doesn't make sense to have these like percentages to scores, because it doesn't work. So don't do that, it doesn't work out well. By the way, often people ask like, okay, tell me about the performance, how much better, how many times is this better than other systems? My favorite comic for this is what you always get when vendors benchmark their tools against their competitors, that under similar conditions, our system is much better than their system. And this is pretty much what they do. That's why we don't have such benchmarks. You can benchmark your own scenario, that makes sense, but don't trust any vendors doing that. And then people have like, I have 1 million documents, it's like an insane amount, and we're always like, yes, 1 million is like when Dr. Evil comes back from the past and asks for $1 million, and everybody's laughing like 1 million is not much anymore. And for us, this is much like, yeah, 1 million documents, that's breakfast. That's not scaring anybody. Okay, to wrap up, we've kind of looked at how storing works, we've looked at how the scoring works, and then there is more. And now it's my time to hand over. Thank you. By the way, if anybody wants stickers, I have a lot of